This video is going to focus on combustion reactions. Combustion reactions is a specific type of reaction that involves organic compounds like carbon, hydrogen, and oxygen that are combining with oxygen and some input energy, and as a result they're releasing a lot of energy in this overall reaction. So here we can see as an example we have C3H8 reacting with O5, so this would be like propane reacting in oxygen, like might burn in your barbecue for example, producing CO2 and H2O. CO2 and H2O are very stable molecules in comparison to the propane, and as a result a lot of energy is released when this reaction happens. Just a couple words I'm going to be using throughout the video that we need to make sure we understand. An endothermic reaction is a reaction in which energy enters the products from the environment, or energy is absorbed from the environment, and as a result these types of reactions make the environment colder. Alternatively, an exothermic reaction is a reaction that produces energy. Energy comes out of the reactants, and as a result the surroundings get hotter. In a combustion reaction we have two phases. We have an endothermic phase in which the fuel for the combustion reaction can get into a state where it is available to combust. If we have something like a piece of wood, this is like a log of wood or something, that log of wood can't combust just like that. What has to happen is that individual particles of that wood have to break off and form little particles of gas. Those little particles of gas can then combine with oxygen and produce a lot of heat. This is a flame, right? And then that's how the burning happens. But the log itself can't burn right as it is. It needs to vaporize in order for that to happen. And so every combustion reaction involves a endothermic part that gets the fuel ready for combustion, and then a combustion or an exothermic phase that uses the ready fuel to combine with oxygen and release energy. Ignition in a combustion reaction is the amount of energy that needs to be put into the reactants, to get the reactants or the fuel ready to combine with the oxygen. In my little example of the log of wood, in the fact that the piece of wood has to turn into a gaseous particle before it can combust, the amount of energy that it takes to take that tiny piece of wood, just a molecule on its own, and get it into that gaseous state so it can combust would be the ignition, or the ignition energy. When we initially start fires, what we discover is if the temperature of the wood is low, then the ignition energy is relatively high in comparison to the amount of energy that's available from the environment, and as a result it can be difficult to get something like a log of wood burning in the first place. The combustion of that wood becomes spontaneous when the temperature created through the exothermic phase of the reaction is enough to provide the ignition energy required for the fuel. So for example, when that little piece of wood turns into a gaseous molecule and then combusts, that combustion releases energy. The question is, does enough of that energy go into making another piece of that wood become gaseous? If the energy released from the exothermic reaction is enough to get another piece of wood into that gaseous state, and as a result it can combust, the reaction can become spontaneous, as that future exothermic release will convert even more wood, and as a result the combustion can become self-sustaining. So one thing combustion or fire requires is an ignition amount of energy to get the reaction started, to create enough energy to make it become spontaneous. In something like a campfire, we would find that we need a fair amount of energy to get enough of the wood into that gaseous state and start the combustion. With something like a gas like propane, all it would take is a spark, a tiny amount of energy to get the reaction started, and it would become spontaneous much easier. This is why when we build our fire, we do two things. We put small sticks at the bottom of the fire, sometimes in a TP shape, with larger sticks of wood over top of them. The ignition energy for the smaller sticks will be smaller, and so getting to the point where the combustion is spontaneous with those small sticks is relatively easy. Once that happens, then the overall amount of energy available may become big enough to get enough ignition on the larger stick and make the larger stick's combustion become spontaneous. So it's easier to get the fire started on the small sticks than the large sticks. So we put those there, and maybe we even take like a sheet of paper all crumpled up and we put it underneath, because that would have an even smaller ignition energy. And so what we try to do is get combustion going with things with small ignition energies, and then they get slightly bigger and slightly bigger and slightly bigger until we get a spontaneous combustion for the overall material. This is only half of the problem. The other half of the problem is oxygen. Not all combustion is complete combustion. If there's lots of oxygen available, if we imagine, for example, propane burning in air, we would need 5 diatomic oxygen molecules to allow that to combust completely and form CO2 and H2O. If there's a lack of oxygen in the environment, it may be what we term incomplete combustion. Incomplete combustion happens when there's not enough oxygen, and as a result we make carbon monoxide, and carbon dioxide while we're burning the materials. Since carbon monoxide is poisonous, very poisonous, this is a very dangerous situation. This is why you shouldn't do things like use your barbecue indoors, because no matter how well your barbecue is running, some of the combustion that happens in your barbecue is going to be incomplete, and as a result it's going to create some carbon monoxide, and if that carbon monoxide is in an area where it can become trapped, it can reach concentrations that are poisonous very easily. So you shouldn't run a gas heater, a gas barbecue, anything like that indoors. Also, if it is indoors and it doesn't have a plentiful supply of oxygen, it's likely to become incomplete combustion faster than if it was outdoors, where the supply of oxygen can be replenished constantly. Note here in this equation for incomplete combustion that it only requires 2 oxygen molecules to produce C, CO, and CO2 versus 5 to do complete combustion, and so we can see incomplete combustion is the natural result of a lack of oxygen. So when we're creating a fire, we have 2 things to remember. Oh, and for what it's worth, complete combustion also produces more energy. So when trying to create a fire, we have a few things to remember. We need our fuel, we need oxygen, and we need our ignition energy. The energy goes into the fuel, and then it allows the fuel to get into a state where it can combine with the oxygen, and that produces more energy. When the energy created is equal to the energy absorbed or greater, then we say that our combustion becomes spontaneous. So that's just a little bit about the chemistry behind combustion, and specifically how combustion works when considering something like a campfire.